All right, so I believe we are recording. All right, so thank you everybody for joining Bonus Learning. And I want to get started, and I didn't want to show you all this before we started, but let's see, let's get to the beginning here. And let me go full screen. All right, does everybody see this title slide?
Yes.
All right, well, I can't see you guys, but please feel free to stop me at any time with questions. And yeah, so the title of today's discussion is Integer Partitions, and it's basically, the way I think about it is like doing math with Lego. And we'll kind of see with these bijective methods and these Ferrers graphs what kind of that means. So to get started, I want to talk about what an integer partition is. So an integer partition of some number n is written lambda partitions n, and it is a finite sequence of weakly decreasing non-negative and non-zero integers which sum to n. So if lambda equals lambda 1 through lambda k as a weakly decreasing list that partitions n with all of the lambda k being non-zero, then a few things that we write is absolute value of lambda is equal to n. We have a len function, which is just the length of lambda, and it's always equal to k, so the length of your list. And we have a max function, which will always be equal to lambda 1. So lambda 1 will always be the largest part in your integer partition. And it'll weakly decrease, which means not every item in your integer partition will be distinct. You can have several of the same number, and it'll weakly decrease, so not strictly decrease. Okay, so for example, if we have n being the integer 5, we can start with the sum of just 5, and we have a single item list in our integer partition in the middle column here of just 5, and another alternate notation is this exponent notation. So this basically just reads we have 1, 5 in our integer partition. So another integer partition of 5 is 4 plus 1, written 4 comma 1, and then 1, 1, and 1, 4 in our integer partition. So we also have 3 plus 2, 3, 2, 1, 2, 1, 3, 3, 1, 1, and so on. And here are the remaining integer partitions of 5. So it looks like we have 7 of them. And this is how we'll denote any single integer partition. And we won't really use this alternative notation until we get to generating functions, but it is also something to note. So any questions so far? Okay, let's move on then. So another thing that we're going to be using during our discussion are these things called Ferrers graphs. They're sometimes called Ferrers boards or Young diagrams. And it's basically just a graphical representation of an integer partition, usually using boxes or dots that are upper left aligned. So for this integer partition, lambda 44211, that partitions 12, the Ferrers graphs can be represented by either of the following. Here on the left-hand side, you see we have the uppermost or upper leftmost row is length 4. Then we have 4, 2, 1, 1. So these are direct representations of integer partitions where each row is the same length as each part. And it's always weakly decreasing as well and upper left aligned. And you can use the dots as well, but I like using the boxes because they remind me of Legos. And one thing that you'll notice is when we start looking at some partition identities is that we can start defining bijective transformations between Ferrers graphs where we start breaking them up and moving pieces around and sometimes adding or removing. And that just reminds me of playing with Lego. So that's another reason why I really like this field of mathematics. So just a few more definitions before we jump into some partition identities. So kind of the big function during this talk will be this function p of n, and it's going to denote the number of integer partitions of a given number n. So this function is called the partition function. And for example, from our table previously, we looked at all the integer partitions of 5, and we noted that there were 7 in total. So p of 5 will equal 7, since there are 7 partitions of the number 5. One thing that we're going to start talking about is partition identities. And they basically always come in the form of the statement, every number has as many integer partitions of this sort as of that sort. And they're usually written in this one-line notation right here, where you have the partition function of n given one condition equals the partition function of n given another condition. So another way to read this is all the integer partitions of n given one condition are the same, or not all the same, but they're all equal to the number of partitions of another condition. And this is usually for n greater than or equal to 1. There are some partition identities that are a little bit more restrictive when it comes to n, but for today's discussion, we're only going to look at non-zero, non-negative integers. So bijection for our case is an invertible function between two sets. And we'll see with these discrete sets that basically we're going to be showing some bijections that are one-to-one in both directions, and that'll be sufficient. And then just a reminder that we have these absolute value of lambda equals n, the length function, and the max function. And yeah, so let's go back to our table. So now I filled out this table a little bit more. We still have all the integer partitions of 5. We have our alternate notations, and I added all the Ferrers graphs for each of these integer partitions. So for the integer partition with just 5, we have one row with length 5. I'm sorry, I shouldn't use the word length, but this row is of size 5. And the total length of the integer partition is 1 because there's only one row, and the max is 5 because the largest part is 5. And similarly, we have 4, 1. The first row is size 4, and then a part with size 1. And then we go 3, 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1, and the one with all ones. And you'll see as we go down the list here, our length is growing because we're adding rows, and our max is decreasing because we're taking boxes from the largest part to make new rows. So I want this to lead into our first conjecture for this discussion. So can anyone look at the last two columns and try to maybe see if there's a partition identity that we can conjecture? What do we notice about these two columns in relation to themselves?
One is the other in reverse.
Yeah, exactly. So that would lead us to our first partition identity, is basically saying that the number of integer partitions lambda of n with the length of lambda equaling some integer k is equal to the number of integer partitions lambda prime of n with the max of lambda prime equaling k. So in other words, we can write this partition identity using our notation here, and this is true for any integer greater than or equal to 1. So going back and looking at these Ferrers graphs, does anyone have an idea of maybe a transformation, like a physical transformation that we could do with these Ferrers graphs that would prove this statement?
Like rotate them 90 degrees? Yeah.
Yeah, pretty much. So what we're going to do is basically take any lambda that partitions n with a length that equals k, and what we can do is just interchange the rows and columns in the Ferrers graph lambda to create this integer partition lambda prime. So for instance, looking at this integer partition here, this is 4, 4, 2, 1. So this partition's 11. And we're going to look at every integer partition of 11 here that has a length 4. We can see if we draw the line y equals negative x, assuming that this Ferrers graph is positioned in the fourth quadrant. And at the origin, we can rotate it around that line and basically transpose it to get an integer partition with a max of that same length. So this is going to be our bijection, because when you transpose it from length k to max k, you can also go backwards from max k to a length of k. And this transformation is actually called a conjugation, and the partition lambda prime is called the conjugate of lambda. Any questions about this proof or this statement? Okay, cool. So a little bit more about conjugate partitions. So we can actually have partitions that are self-conjugate, and it basically just means if you conjugate it, you get the same exact Ferrers graph. So we can look at the self-conjugate partitions of 12, and there's 3 of them. It's 6, 2, 1, 1, 1, 1, 5, 3, 2, 1, 1, 4, 4, 2, and 4, 4, 2, 2. So you can see there's some symmetry here, and we would call these partitions self-conjugate. And there's actually a natural way to transform these self-conjugate partitions into partitions with distinct odd parts. So this is going to lead us into our second partition identity for today. So the number of integer partitions that are self-conjugate of n is going to be equal to the number of integer partitions with distinct odd parts. So that means every part on the right-hand side is going to be of odd size. Sorry, my dog is going to be barking throughout this whole thing. And, oops, gave away too much there. And so each part is going to be of odd size, and each part is going to be distinct. So let's see. Let's go right into the proof here. So basically, to prove this identity, what we're going to do on the left-hand side, we're going to be starting with these self-conjugate partitions. And we're going to take the first row with the first column and make a new row of all these boxes. And then we're going to go on to the second row and second column and merge them into a new row. Since we're starting with the self-conjugate partitions, we're always going to merge a row with a column that has the same length. And since they share one box, the result is going to be a part that is twice the size of the row minus 1, so hence odd. So you can see here, if we start with the first row and the first column, basically what we're doing in this transformation is unbending that piece or that part, and we're making it into one long odd size part on the right. And then we're going to move on to the green part, do the same thing, and then with the red part as well. So you can see that starting from a position with distinct odd parts, we can also bend each row at this median position. And since each piece is odd, it'll have that. And we can bend it into a unique symmetric hook. And then we can fit them inside each other to form a self-conjugate Ferrers graph from these partitions with distinct odd parts. So this is the bijection that will prove the identity. And the thing to notice here is that we're definitely pairing up every self-conjugate partition of n with a unique partition of n that has distinct odd parts. So any questions about this proof or this bijection?
I'm thinking there's another bijection we could get that kind of turns these odd ones into partitions of smaller integers.
Yeah. So that's a good catch.
Thing?
Yeah. So there's actually we'll see when we get to generating functions too that a lot of these ways that we're counting the partition function can have many bijections into other to other conditions as well. So it's not unique that all of these self-conjugate ones have to be paired with distinct odd parts. There might be other bijections that pair it with the same amount of partitions of n that have a completely different condition as well.
Right. So it sounds like there's more robust methods that are going to elucidate that a bit.
Yeah. Yeah. Exactly.
Cool. Thanks.
Yeah. So moving on, I wanted to throw in some fun identities for you guys to prove. Now that you guys have the fundamentals of integer partitions and Ferrers graphs, you can come up with bijections to prove any one of these statements here. And we're actually going to see Euler's identity later on when we get to generating functions. So I'll send out these slides at the end of the meeting, and if you guys feel like a good puzzle, then you can try these. And now, excuse me, we're going to get to a proof for Euler's pentagonal number theorem. So the theorem with respect to integer partitions is that the number of integer partitions of n that have an even number of distinct parts is equal to the number of partitions of n that have an odd number of distinct parts, plus this error function. So E of n is going to be plus or minus 1 if n equals this funky expression here. And we'll see pretty soon that this expression here is related to pentagonal numbers, and for just for some integer j. And otherwise, it is just equal to 0. So unless n is a pentagonal number, then we won't have any error issues. So let's jump right into the proof, or setting up the proof. So I think the name of the theorem is a good place to start, and an even better place to start is with the triangular numbers. So the triangular numbers are the numbers 1, 3, 6, 10, and so on. And they can be represented by the following sequence of Ferrers graphs. So we have the first Ferrers graph, which is just 1. Then we have 2, 1, which is 1 plus 2 or 3, right? And you can see we're adding a row to the top that is 1 greater than the previous rows. And that's how we derive the triangular numbers. So these are the Ferrers graphs for the triangular numbers. And we actually have a formula for the jth triangular number, which is just the sum of all the integers between 1 and j, which is j times j plus 1, all divided by 2. So similarly, the pentagonal numbers are 1, 5, 12, 22, and so on. And they can be represented by the following sequence of Ferrers graphs. So here we have 1, and then 3, 2. This one is 5, 4, 3, and so on. So can anyone see a relationship between the triangular number Ferrers graphs and the pentagonal number Ferrers graphs? Let me see if I can show you here. Here's the triangular.
Well, yeah, it looks like they're like you took a triangular number 1 and then one that was maybe a little less than half that size and chopped that size off. Like you took one and subtracted the other kind of thing.
Yeah, pretty much. So our first observation leading up to the proof, so the jth pentagon actually consists of the jth triangle next to a rectangle of width j minus 1 and height j. So you can see here in this first column, we have the first triangular number and then no rectangle because the width would be j minus 1 or 0. Here we have the second triangular number plus a rectangle of width 1, height 2. Third triangular number, width 2, height 3, and so on. So, excuse me. Therefore, the jth pentagonal number, we can find a formula for it to be just the dimension of that rectangle, so j times j plus 1 in blue, plus the triangular number j times j plus 1 all over 2. And this actually simplifies to j times 3j minus 1 over 2, which is actually one of the conditions for our error function here. So this is going to come up a little bit later. So our next observation is that the Ferrers graphs of these pentagonal numbers, sorry guys, they come in distinct parts, right? So every pentagonal number is actually going to meet one of the conditions for our original statement, right? Whether a partition comes in an even number of distinct parts or an odd number of distinct parts, right? A pentagonal number will meet that criteria. So these particular partitions, like we said earlier, they're going to be special cases in this following proof. Sorry. Hold on one sec. All right, we're just going to go through it because I don't know what to do about it. I'm home alone. So our goal for the proof is going to be to try to create a bijection, just like we did in the previous partitions, partition identities, that will partition the even number of, or the partitions of n that have an even number of distinct parts on one side and partitions of n into an odd number of distinct parts on the other side. So let's get into the proof. So this proof found by Franklin in 1881. And we start by, we would basically like to describe an invertible transformation that will change the number of parts by 1, hence going from even to odd or odd to even, but also keeping the distinctness of the parts, right? So we have to make sure that when we make this transformation, that we're not mapping to integer partitions that do not have distinct parts, right? Or an even or odd number of distinct parts, right? So for a first approach, kind of keeping this idea in mind that we want to change the number of parts by 1, why don't we take the smallest part and distribute its boxes to the remaining rows, basically until we run out. So here on the left, I'm going to take the smallest row, I'm going to break the Lego off, and I'm going to start padding the right diagonal, right? So this idea that we're removing one part, so hence changing from even to odd, and trying to keep distinctness by padding distinct parts by at most 1. So we're not going to lose distinctness, right? So in this second one, we're doing the same thing. We're going to take the bottom row, which is size 3, and pad the right diagonal. And you'll see if we're not directly on the diagonal, that we're going to jump to the next row and just keep going until we run out of boxes. And again here, even if there is no row to pad, we're just going to create new rows as we go down. So pad the diagonal and then keep padding, and then creating new rows until we run out of boxes from that smallest row. Now, this is a good first start, but does anyone see any issues with this approach?
The final diagram doesn't have distinct parts.
Yeah, it's not distinct. Like, it's okay to have non-distinct parts, but we want to make sure that we're changing the number of distinct parts from even to odd, or odd to even, right? So here we're going from 3 distinct parts to still 3 distinct parts, which is not good. And another thing to notice is that these two starting partitions right here are different, but they map to the same exact integer partition. So we can immediately say that this transformation is not 1-to-1. So it's not going to work for our bijection, but we might still use it in certain cases, right? Is there any questions about that so far? Okay, so just keeping in mind that our goal is to change the number of distinct parts by 1, and also keeping distinctness by padding each row by at most 1. So good start, but why don't we go in the opposite direction by taking all the squares in the rightmost diagonal and then making a smallest row. So kind of the same idea, but backwards, right? So here we're only going to look at the rightmost diagonal. So on the previous slide, we kind of just kept padding until we ran out of boxes. But now we're going to restrict our attention to just the rightmost diagonal and all the boxes that intersect, right? So here I would only take these 2 red boxes, break off the Lego, and make a new smallest row. So here we're definitely going from, well, here we're definitely adding a new distinct part to this integer partition. So we're pairing something with an odd number of distinct parts with an even number of distinct parts, or vice versa. Excuse me. So this is going to seem to work. And we can actually define our bijective transformation to be a combo of the 2. So we're going to define it to be as follows. We always want to remove the rightmost diagonal to form a new smallest row. If the diagonal is longer than the current smallest row, then we're going to go back to the original transformation and then take the smallest row and then pad the right diagonal. So you can imagine a case where, even if we just started with this one right here, this rightmost diagonal has size 3 and our bottom row is 2. So in this case, we would move the bottom row and pad the right diagonal, getting us back to this one. So it's definitely a 1-to-1 pairing. All right.
So that condition, if the diagonal is longer and you have to do something different, is that what you do instead of removing from the diagonal, or in addition to?
You do it instead.
Thank you.
Yeah, no problem. So it basically guarantees this opposite direction, right? So in this case, we have the diagonal is longer than the bottom row, so we're going to go backwards. And these, in fact, pair with each other. I should have used the double-sided arrow here, actually. Can you guys actually see my cursor when I move it around the screen? Or no?
Yes.
Okay,
Yeah.
good.
I do have a question. So in this case, it's self-inverting.
Mhm.
Is it always?
Yes, but
Okay.
there's going to be some cases that we're going to run into, hence the pentagonal numbers probably, that have these error conditions. So that leads us to our next question. Can we ever imagine a case here where either the transformation of removing the diagonal and padding the bottom row, or not padding, but adding a new row, or removing the bottom row and padding the right diagonal doesn't produce a valid Ferrers graph? And basically the answer is going to be when we have those pentagonal numbers. So there's two cases, and we'll explain them in words, and then I'll show you some pictures. It's basically when the shortest row will intersect the rightmost diagonal in the lower right corner of the graph, and it is the same length as the diagonal. And another case is when the shortest row intersects the diagonal, and the smallest part is one box longer than the diagonal. So visually, we have those here. So here's case one, where the diagonal intersects the smallest row, and the smallest row is the same length as the diagonal. And here, we have the diagonal intersecting again, and the smallest row is one box longer than the diagonal, right? So it's not a problem if the smallest row is 2 or greater than the length of diagonal, because then you can just take the diagonal off and pad the bottom. So here, if we were to take the diagonal off, we wouldn't be able to make a new smallest row because the smallest row is 2 and this one has size 3. And here, if we were to remove the diagonal and make a new row, then we'd have 2 rows of size 3, which is okay, but it's not adding or removing a distinct part. So we're not going from even to odd, right? So, and these Ferrers graphs match the pentagonal numbers that we looked at in the beginning. All right, so in case one, these are just the legit pentagonal numbers with size j times 3j minus 1 over 2. These are pentagon-like, but with an extra column. So this is the reason for that plus or minus condition in our statement for the error function. So the pentagons in the second case, they have an extra column in the rectangular parts, and that gives their total size of j times 3j plus 1 divided by 2. So basically, this describes the transformation that we want, except for these pentagonal partitions. And this transformation, whether you're removing the diagonal and making a new row, or removing the row and padding the diagonal, will pair every partition of n into an odd number of distinct parts, and a partition of n with an even number of distinct parts. And then if it just so happens that the n that you're looking at, you're going to run into these cases, either case 1 or case 2, where j is going to be even or odd. And in those cases, you're just going to be adding 1 or removing 1 from the total number of odd distinct parts. And that basically proves the theorem. I know it's a little hand wavy and stuff like that, but for the most part, that's the meat and potatoes of the proof. Any questions so far?
I'd like a little more clarification on what the transformation is. Like if you could do some, apply it to some more partitions, particular edge cases like 1, 1, 1, 1 or something.
Yeah. I don't have any obviously in here, but remember when we start, we're only going to be looking at the partitions of n that have a distinct or an even number of distinct parts, right? So those edge cases that you might consider might not even be part of the set that we're looking at for our transformation. So 1, 1, 1, 1, 1 would have an odd number of distinct parts, And in that case, I guess, let's see, what would we do? The rightmost diagonal would be, no, in that case, I guess we would take the smallest row, which would be the bottom part, and pad the right diagonal, I believe. But we can look at these ones right here and what we would do in this case and make sure we have broken this not one-to-one situation here. So here we would take the rightmost diagonal, and since it's longer than the bottom row, instead we would take the bottom row and pad the right diagonal, getting us to this partition here. Now here we have a rightmost diagonal of 2, and since it's shorter than the smallest part, we would take the rightmost diagonal and make a new smallest row. Oops. So that would immediately break this being mapped to the same partition here. And then here, again, we would have a rightmost diagonal of length 2. So we would break it off and make a new smallest row and not go here. So now we're definitely adding a distinct row instead of adding 2 rows of the same, which would just take an even number to an even number or an odd number to an odd number.
Yeah, cool. Thanks for verifying that. My last question about the definition of the rightmost diagonal, if the first 2 parts are of equal size, is the rightmost diagonal considered to be starting with the top right box or the one below it?
You know, I think in that case, we would consider the rightmost diagonal to be of size 0, kind of going back to your edge case of the 1, 1, 1, 1, 1. And in that case, we would always take the bottom row and pad the rightmost diagonal. Does that make sense?
Okay.
Good questions. So getting, okay, so that ends the proof of how we doing on time. I can't see the clock.
You're halfway through.
Perfect. So now I want to move on to generating functions. So to begin our discussion of generating functions and how they relate to integer partitions, I want to suppose a scenario where we want to find all of the possible partitions that consist of 1 even part and 1 odd part, and each of them is strictly less than 7. So there are actually 9 of them, and we could just write them all down, but one way that I want to show you guys is that it naturally arises in polynomial multiplication. So basically what I can do is I can take 2 polynomials and construct them in a way such that this first factor has all even exponents that are strictly less than 7, and then the second factor will be all odd integers strictly less than 7, right? And one thing that I want to stress during this section is that each term in the resulting multiplication comes from choosing a term from each factor and multiplying them out. So if we wanted to get this first term, we'd have to choose q squared and choose q to the first power, multiply them together to get q to the 2 plus 1, right? And then the same with 2 and 3, 2 and 5, and for every possible choice that you can, but you have to choose one from each factor, will result in these 9 terms here. And what do you guys notice about the exponents in the second line? Think about our conditions for the integer partitions that we're looking at.
I was going to say they're all odd.
They're all, in the result, they are all odd, but in the second line, one thing to notice is that they're all integer partitions that have 1 part that's even, 1 part that's odd, and all of them are strictly less than 7, right? So this second line is actually going to show us all of the integer partitions that meet our criteria, right? And in the third line, it actually shows us a little bit more. So the second line exhibits in the exponents all the partitions with 1 part even, 1 part odd, and all of them are less than 7. And that's just by design, because we chose our factors to be polynomials with strictly even and strictly odd integers less than 7. And this function has a name, and it's called a generating function for this particular coefficient, or sorry, for this particular partition. And furthermore, on the third line, it tells us a little bit more. So the coefficients of q to the n is the actual number of such partitions of that exponent n. So if I were to restrict this search to, I want to know how many integer partitions are there that have one even part and one odd part that are strictly less than 7 of the integer 3, well, then I would look at the coefficient. And since there's 1, then I know there only exists one integer partition, namely 2 plus 1, that meets that criteria. If I were to ask the same question about the integer 5, then I would look at the coefficient, and the coefficient would tell me that there's 2 ways to do this, namely 2 plus 3 and 4 plus 1. The same with 7, I can ask the same question, and there's 3 ways, 2 ways for 9, and 1 way for 11. So does that make sense? Any questions so far?
I'm wondering where you got like the first 2 polynomials that you multiplied together.
Yeah. So it's kind of going to lead us into like a broader discussion about it, but we'll kind of see how these integer partitions relate to infinite products and even infinite sums. So that's actually going to come up in the next slide. So this leads us to our first theorem. So getting back to the partition function, P of n. So if we have the partition function P of n and we let q be an indeterminate, then the infinite sum from n to infinity of P of n times q to the n equals the infinite product from k equals 1 to infinity of 1 over 1 minus q to the k. So let's get to the proof. So the cool thing about this, so the first time I saw this was in a discrete math class, and I thought it was really interesting that we were looking at infinite sums and products in a class called discrete math. This totally changed my perception of infinite sums and series and stuff like that. So basically what we can do, since we're choosing q to be an indeterminate, we can start using things that we know about geometric series and stuff just by assuming that the indeterminate is absolute value less than 1, right? So basically the indeterminate doesn't do anything for us. It just allows us to use these nice infinite sum and product theorems, and basically the only thing we care about is the coefficients, right? So usually the coefficients will help us count something. In this case, how many integer partitions of n, right? So looking at the proof, we can rewrite this infinite product. Looking at the first 3 terms, these look like geometric series, right? This first term where the common ratio is q, second one q squared and q cubed, and so on. So we can rewrite these as infinite sums, right? 1 plus q squared, and so on, right? The second one where our common ratio is q squared, right? And q cubed, and so on. So Nate, this is where we get the kind of relationship to these polynomials. And depending on the situation and what you're trying to count, we can restrict this or rewrite it in a different way. So does everyone see how these first 3 terms translate to the geometric series? Any questions?
So is it true that on your example on the previous slide, you were multiplying only 2 polynomials because you were looking at integer partitions with only 2 parts?
Exactly, and we had some even further restrictions, restricting each part being less than 7 and stuff like that. So
right, you don't have to do an infinite polynomial.
Yeah, exactly. So here, this would be the general expansion for just looking at the partition function of any number n given no conditions whatsoever.
Great.
Yeah. So basically, what this all comes down to is what we did in that first example. This polynomial multiplication, it all comes from choosing a term from each factor, right? So if we were to select a factor, say q to the k, from the kth factor that had an exponent of mk, right? We're gonna select one from each parentheses in this infinite product. Then each term in the expansion of this product is going to be of the form of, well, how many q1s did you choose? Well, I chose m1 of them. How many q squares did you choose? I chose the m2 term. I chose the m3 q cubed terms, and so on. So this is also an infinite product, and these exponents just relate to which one you chose to multiply from each factor, right? And there's actually a one-to-one correspondence between these terms and these infinite products into integer partitions written in that alternative notation that we looked at in the very beginning, where, well, how many ones do you have in your integer partition? Well, I have m1 ones. How many twos? I have m2, 3, and so on, right? So choosing a term from each one of these factors in this infinite product is in one-to-one correspondence with building an integer coefficient, or I'm sorry, an integer partition with these exponents as the number of parts that you have of that particular integer. And the result follows since the size of the integer partition is namely, well, how many ones do you have? I have m1 ones, m2 twos, plus 3 or m3 threes, and so on, building us to n. And this will match the exponent of q in this infinite product up here. Okay, so that's kind of a lot of notation thrown out right away, but again, I want to hammer home that idea of just choosing a term from each factor. Will build an integer partition like this, right? Where this first factor right here will be choosing how many ones you want in your integer partition. These will be how many twos you want, and these will be how many threes, and so on. Any questions? Okay. So this leads us to a corollary of that first theorem, GF1. So now we're going to start putting some restrictions on these partition functions. So we can actually write the infinite sum of the number of partitions of n that have strictly distinct parts times our indeterminate q to the n as the infinite product 1 plus q to the n. And looking at the proof, since all of the parts must be distinct, so in this case, you can't have multiple parts of the same size, then the integer partition must look like the following, where you have m1 ones, you have m2 twos, m3, and so on. But all of these mk's have to be 0 or 1 because of this distinct condition. And that basically just means we can't have more than one piece of the same size, right? So it follows from our first theorem that the factors that make up the infinite product are, excuse me, these guys, where this first factor asks, well, how many ones do you want, how many ones do you want in your integer partition? Well, choosing 1 will give you 0, and choosing q to the 1 will give you 1. How many twos do you want? Choosing 1 will give you 0, and choosing q squared will give you 1, right? So you can only have 0 or 1 of a part of a particular length or a particular size. So that gives us the infinite product from our statement. Is everybody okay with that? Any questions? Okay, let's move on. And this is going to lead us to Euler's identity, which is actually a partition identity that I put on that slide that I left for you guys. And Euler's identity states that the number of integer partitions that have distinct parts of n equals the number of integer partitions of n that have parts that are all odd, again, for n greater than or equal to 1. So basically, we're going to use that corollary that we just proved, that we know that the partition function with this condition that parts need to be distinct can be written as this infinite product of 1 plus q to the n, right? So basically what we can do is we can look at the infinite product and kind of manipulate it in a way algebraically that'll get us to a statement that uses our first theorem that showed how we represent these partition things as infinite products. So what we're going to do is we're going to expand. So I couldn't get the Beamer slides to like pause in an align environment. So this whole proof is just going to be visible on the next slide. But we'll go through it line by line and see what happens. So basically, we're going to start with our infinite product that represents integer partitions with distinct parts, right? And we're going to expand it. We're going to expand it through the first 6 terms here just to illustrate our point. So we have 1 plus q times 1 plus q squared, and so on through 1 plus q6. So what we're going to do to each term now is we're going to multiply it, and I kind of stated it here. We're going to multiply it by 1 minus q to the k over 1 minus q to the k for each one of these terms, basically giving us a difference of squares in our numerator, and then just a single factor of 1 minus q to the power for each term in these subsequent lines. So now we've rewritten this in a way that each one of these, if we look at just the denominators, we have factors that have 1 minus q, 1 minus q squared, 1 minus q cubed, and so on. So you'll see that these exponents are going up sequentially, and the exponents in the numerators are going up by 2, right? So we have all of the evens in the numerators, and we have every number in the denominator. So we get this telescoping effect where we can cancel every term in each numerator with basically every other term in the denominator, right? So all of the evens will disappear, which is going to leave us with just the factors of 1 over 1 minus q over 1 over 1 minus q cubed. And you'll see that as the infinite product goes on, each one will have an exponent that's odd, right? And this actually, if we were to rewrite it as an infinite product, is written like this, where n is odd. And this actually matches our statement right here. And this will allow us to prove that in fact that infinite product represents all the partitions of n such that all the parts are of odd size. And that's it for that proof. And are there any questions? I know I kind of rushed through this last one a bit. Let me change.
I don't have any questions about the last part. That was really cool and well presented.
Oh, cool. Thanks.
Do you know the original motivation behind defining pentagonal numbers? Like, is this the primary use of a pentagonal number? It seems a little bit less concise than a triangular number.
One thing I guess I didn't mention was, so I did say in my description of the talk that I was going to have 2 proofs of Euler's pentagonal number theorem, but I actually only had 1, and this is actually not, this last one is not related to pentagonal numbers at all. But were you referring to the original integer partition one where we looked at pentagonal numbers?
When we were looking at the issues you run into and have to have an error term for pentagonal numbers. I was just curious why a pentagonal number exists in the first place. Like, we observed some things about them, but I didn't get what the original definition was or why they were defined that way.
Yeah, so normally people like to do them. Let me show you actually a pretty cool description. I've seen some really cool images for them. I chose to show them with the with the Ferrers diagrams, but a lot of people like to show them, I guess, this way, where there's like the dots on the pentagons. So this is where the pentagonal numbers come from. I think they're even in Pascal's triangle a bit, but I chose to basically just do 1 and then 5, and then basically you get every pentagonal number by going down one further dot and adding up all the ones on the pentagon. I'm not sure like how this got, like how Franklin thought that these were related to pentagonal numbers like at all, or I guess like he was just trying to find bijection and noticed like the one that he was trying to show broke down with these pentagonal numbers. And it's funny because the other ones aren't even pentagonal numbers. They have that extra column there. But anytime this statement is shown in integer partitions, it's always stated as Euler's pentagonal number theorem, which is, interesting, I guess. Oh, I didn't even see all the comments here. Sorry, guys.
So I'll mention the last class that I taught was a history of math class, and apparently the Greeks studied what are called figurate numbers, right? So famously triangular or square numbers, but like you could just keep going. The pentagonal numbers are really interesting. There's like 2 different kinds, which I'm not sure. You might know, buddy, that like that there's that plus or minus term in your theorem that I'm wondering if that was like the first kind and second kind of pentagonal numbers.
Yeah.
There's some connection between them with the generating function that I've heard called Euler's pentagonal number theorem before. So it might be like a different form of that result. I'd be lying if I said I remembered anything about it, just the cultural awareness, and I remember there being 2 different kinds of them. Like those are really interesting for some reason.
Yeah, so the next example that I wanted to put in there, but I thought I had too much, to be honest, was the generating function proof of Euler's pentagonal number theorem. So I have that in my book here. I can take a photo of it and send it to you guys, and it's really similar to what we did in the last example, with just manipulating that infinite product to kind of represent those geometric series being all multiplied together. And it's pretty cool, so I'll definitely send it out. But
Yeah,
other than
that really clarified, like the traditional diagram for pentagonal number makes it obvious why it's called that. The Ferrers diagram is a little funny looking for pentagonal number.
Yeah.
I just wanted to comment that it's very insightful to use infinite sums and products that way. Like, I feel like that you've shown that to us. I could do a couple of your extended problems, but I never would have thought, oh, the easy way to do this is to introduce polynomials. Yeah,
and that blew me away when I first saw it, and now every time I look at it, infinite series, I totally look at it differently. I got a ton more cool stuff I can show you guys. Actually, one of the books that I used was a book written by my advisor, and it's called Counting with Symmetric Functions. So he gets into a ton of stuff where you start using some abacus or abaci to use counting functions, and then he gets into these really cool things called bijective involutions, which are where you start using like bricks and ladders, which are just diagrams, and you start filling them with numbers, and you can prove all sorts of crazy stuff and really cool counting problems. So it's awesome stuff. I'll share it with you guys. Other than that, that's all I have for you guys. So thanks for sticking around. This was fun.
Thanks, buddy.
Yeah, thanks,
everybody.
Thanks for speaking. And yeah, I thought it was really interesting, and your arguments were really like clearly presented.
Oh, thank you. Appreciate it. I'll see you guys in chat.
See ya.
See ya.